Okay, so continuing on to the last topic of this section, we now discuss the curvature. So given some curve represented by a vector valued function, we want to have a measure of how sharp the turns along the curve are. Scrolling back to the diagram of a curve on the first page, right? So imagine you're traveling along the curve. So like this portion of the curve is fairly straight. So the curvature is small. And here there's a much sharper turn here, and then it straightens out. Again, here the curvature is small, and then here there's a larger bend. So there's more curvature here, right? So we basically along the curve, we want to measure the sort of how the curvature changes as you travel along the curve. So the formula for calculating the curvature is here. So the formula itself, the derivation of the formula is somewhat complicated, so we won't really go into detail there. So I'm just going to present this formula and say this is the formula that you want to use to calculate the curvature. One thing to be aware of is that if you have two different parameterization for the same curve, you want the formula for the calculating curvature to be independent of the different parameterizations, and this formula is independent of any parameterization. It's just that the formula itself is not obvious that it is independent, even though it is. So in actuality, there's actually a different definition of curvature written here involving the unit tangent vector, and this s in the denominator is referring to something called the arc length function. If you take the integration so that the lower limit of integration is the left endpoint, but you allow the right endpoint of integration to vary with the parameter t, then this gives you the arc length function. So there's actually a slight mistake here, because if I'm using the variable t here for the arc length function, this variable has to be a dummy variable. So I mean, you have to use a different variable. So this would be like u or something. But in any case, this would be the arc length function, where basically this calculates how the length of the arc increases as you move along the curve. But anyway, you set up this calculation here, and then this calculation also gives you the curvature. However, so this formula here is independent of any parameterization, but typically it's very difficult to calculate with this formula, and so that's why the formula in the box here is the one that I'm telling you to use to calculate the curvature. Okay, in any case, let's take a look at example 3, and here we calculate the curvature. So let me add another page after this, because probably this is not enough space to set up the calculation. Okay, so this is my curve, r of t, right? So in the curvature formula, we have to calculate both the first and the second derivative. It also involves a cross product, and we have to calculate some magnitudes also. So there's quite a bit involved in the calculation. So let's first start off by calculating the first and the second derivative. So the first derivative, here we use the chain rule. So the -2 comes down, you get -2e to the minus 2t, and then the derivative of 2t is just 2, and then the derivative of a constant is 0. Okay, so that's the first derivative. And then now we calculate the second derivative. So again, here, the chain rule, the minus 2 comes down. So negative 2 times negative 2 gives you 4. So you get 4e to the minus 4t, comma, the derivative of constant, again, is 0. So that's 0. And then this is also 0. Okay, so that's r prime and r double prime. And so the next thing to do is to calculate their cross product. So r prime cross r double prime. Okay, so before we calculate the cross product, we can I mean, there's two ways you can do it. I can calculate the cross product in terms of the functions with the parameter t, but because we're asked to calculate the curvature only at a single point and not over the entire curve, this makes the calculation a little bit easier, right? So I can plug in the t value now instead of later, right? So at t equals 0, you get r prime of 0, so you just plug in t equals 0. So e to the 0 is 1, so this is just negative 2 to 0, and r double prime of 0. Again, the exponential of 0 is 1, so you get 1 times 4 is 4. And so again, because we're asked to calculate the curvature only at a single value of t, we can just calculate it in the beginning, and then that'll make the cross product easier to calculate. So I don't have any more t's involved, right? So now these are just numbers. Okay, so let's proceed. So we want to calculate r prime cross r double prime. So we set up the determinant. So I, j, k. Second row is r prime, so you get negative 2 to 0. Third row will be r double prime, so that's 4, 0, 0. Okay, so now we just expand this, right? So here this will be 2, 0, 0, 0, I hat minus, and then for j it's this, 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 so minus 2, 0, 4, 0, j hat, and then plus for k, for k it's this, 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 so minus 2, 2, 4, 0, k hat. Okay, so then what do we get? This determinant is 0, so that's just 0. This determinant is also 0, so this is also 0. And then this last determinant, so 0 minus 2 times 4, which is 8, so that's minus 8. Okay, so this is what we get for the cross product. And then now what do we need? We need a magnitude in the numerator and also a magnitude in the denominator. So the magnitude of this is just the magnitude of this vector, right? So square root of 0 squared plus 0 squared plus a negative 8 squared. So that's just the square root of 64, which is equal to 8. Okay, I'm just going to try to squeeze it into this little space here. In the denominator, I have the magnitude of r prime to the third power. So what is this? So you have the sum of the squares, but the magnitude has a square root, which is to the 1/2 power, and that's also raising to the third power, so the whole thing is going to be to the 3/2 power, right? So which one is r prime? R prime was this one, so that's negative 2 squares. So you have the sum of the squares, squared plus 0 squared. And then again, you have this third power, but the magnitude also has the square root, so that means 1/2 power. So you have this thing raised to the 3/2. So what's inside? So this is 4 plus 4 is 8. So this is 8 to the 3/2 power. And then finally, the curvature is just this number divided by this number. So 8 divided by 8 to the 3/2. Let me give myself a little bit of space here. So kappa is equal to 8 divided by 8 to the 3/2. And this is equal to about 0.3536. Okay, so that's how we calculate the curvature. I mean, so again, this problem was slightly simplified because again, we're only asked to calculate the curvature for a single value of t. So that means that you can just calculate these quantities for t, and then the rest of the calculations doesn't involve t any longer. If the problem were different and you were asked to calculate the curvature for the entire curve, then all the calculations here will typically involve the variable t, right? So you have to do the calculation leaving it in terms of the functions. Okay, so in any case, that's how we calculate the curvature.